Welcome to this video. We will discuss unsupervised learning, and more specifically we'll talk about clustering. In contrast to supervised learning, where we provide the machine learning model a pair of the x and the y, the feature matrix and the target outcome, in unsupervised learning we only have a feature matrix. And the goal of the unsupervised learning algorithm is to uncover some hidden structure within this feature matrix. One example application is clustering, which is basically associating different observations to different clusters based on the similarities of their feature values. In this lecture, we'll talk about an algorithm called k-means clustering. K-means clustering creates, as the name implies, k clusters, and it creates the k clusters by uncovering their means, which is basically a point in each cluster which is close enough to all of the data points associated with this cluster, but farther from the data points associated with other clusters. Let's take a look at an example here. In this example, we're simulating an artificial data set. We're basically creating a data which looks like it's composed of 4 clusters, and those are the blobs of points. Each one of them has 75 points. So in total we have 300 observations, but we constructed these observations to be kind of belonging to 4 clusters. Of course, in this example we're simulating the data, so we know the true association in between each data point and its cluster. What we're going to do now, we're going to use the k-means algorithm, and we're going to fit the x. Now, in contrast to fitting a supervised machine learning model, you can see that the fit function, it only takes the x because there is no y. Once we do the fit, we can actually predict the cluster that each data point belongs to. I'm putting the cluster back to the data frame, and as you can see here, in the new data frame, I have now another column called cluster that has the cluster that each point belongs to. Now, we're going to visualize the clusters now. What I'm going to do here, I'm going to take the centers of each one of these clusters. Let's run the data here. If you take the centers of each one of the clusters, that should give us an idea about the center location of each one of the clusters. You can see that cluster 1 has a center point at 0.15x and 2.8 on the y. The second cluster is at minus 1.37 on the x and 7.75 on the y, and so on and so forth. What I'm doing here, I'm basically creating 2 plots. One of them is basically plotting the data itself. That's chart 1. The second plot is plotting the cluster centers, and I'm plotting them as red circles. And then I'm putting chart 1 and chart 2 on top of each other. So what we have now, if you take a look, you can see that each one of these observations has an encoded color which maps to its cluster, and the center of the cluster is also put on top of those points. So we can see here that the algorithm, the k-mean clustering, basically uncovered the hidden structure in the data. This data was created in a way that it had 4 clusters, and we actually managed to uncover those inherent clustering in the data itself. You can also see that each one of the cluster, if you take a look at the mean, it's basically a point which is closer to each point in the cluster. So each point in the cluster is closer to the cluster mean than any other cluster mean. So if you take a look at this point, it should be closer to this red point compared to this red point. This is indeed how the k-means clustering algorithm works under the hood. Under the hood, it's an iterative process. It starts with a bunch of random cluster centers, and then it calculates the distance between each point to each cluster center and creates an initial clustering. Now, from this initial clustering, it readjusts the centers of the cluster to be closer to the average of all of the data points here, and it then iterates one more time so that it improves on this initial clustering. Those two steps are called expectation maximization, and this general algorithmic strategy is used in many machine learning algorithms. We're not going to worry about what's under the hood in the k-means clustering algorithm. What's important to us is to understand its limitations, as well as some of the hyperparameters it takes. Obviously, the most important hyperparameter is the number of clusters. Notice that this is something we need to provide to the k-means clustering, so that it knows how many clusters to expect in the data. In the previous example, I provided a value of 4, which basically matched the true number of clusters in my data here, right? And that's why the clustering itself was pretty good, because I already provided the true number of clusters in the data. However, if I provide a different number, the clustering may not be as good as in the previous case. Like for instance, if I create a clustering using 6 clusters instead of 4, notice what we see here. You can see that those clusters have also their centers, right? And the same criteria applies, right? Each one of these yellow dots is closer to the center of the cluster than any other cluster. Now, this is not as good as in the previous clustering, and we can see that when we visualize it, but the k-means algorithm has no way to make that assessment. We can see that those two groups, the red and the blue, are should be grouped together, then the green and the light blue as well, but the k-means clustering has no way to make that assessment. So the number of clusters is one of the hyperparameters that we need to provide to the algorithm. Another limitation of the k-means clustering is that it's limited to linear boundaries, clusters that have linear boundaries, meaning I can separate this cluster using a line if I have 2 variables, or a plane if I have 3 variables, or a hyperplane if I have more than variables, but they have to be linearly separable. In this case, for instance, I can draw a line here, a line there, a line here, and a line there to break or separate these clusters. Because I'm using the average of the points, I'm expecting this average to be closer to the points, which means the data itself is convex. If the data is concave, such as in this example, there is no linear boundary that separates the two clusters, and the k-mean algorithm will make a mistake when trying to separating them. So we're simulating another data set, and this data set has kind of like 2 moons, 2 crescents here, and this is a concave kind of 2 clusters that have a concave boundary here, and it's not possible to separate these clusters by any linear line, by any line, right? Any line that you draw is going to cut through them. And even if we supply the right number of clusters with the k-means, it's not going to have a satisfying clustering here, as you can see, because it's kind of determined that the blue points, which are close probably to a center here, are closer to the center of the cluster than the yellow points, right? Now, scikit-learn contains many more clustering algorithms. And if you take a look at the API itself, these clustering algorithms are some of the clustering algorithms are much more useful depending on the structure of the data. We're not going to go into the details of the clustering algorithm, but for instance, if our data is concave, such as in this example, an algorithm called Spector's clustering can do a much better job than the k-means algorithm. Another disadvantage of the k-means is that it can be also slow for a large number of clusters. Once again, there are other algorithms that may serve us better if we have a large dataset and large number of clusters. Now we're going to apply the k-means algorithm to cluster the cars dataset. So we have seen this dataset before, and this dataset we used a regression model in order to predict the fuel efficiency, the miles per gallon in the car. Let's assume we don't know the miles per gallon. Is it possible to structure the data somehow to see how different groups of combinations of the other feature matrix can relate to the miles per gallon? That's what I'm doing here. I'm creating a k-means clustering using 3 clusters, And I am using two variables as two features, the weight in pounds and acceleration. Now again, I only chose three variables because I want to draw the clusters on, visualize it on a two-dimensional space. Obviously, I can increase the number of features here if I wish. For illustration purposes, let's say I want to cluster my database on the weight in pounds and acceleration. So I'm going to predict the clusters. And what I am doing here, I'm replotting the data using the point graphical mark, but I'm using the shape encoding to denote the cluster. So as you can see here, I have three clusters: triangles, circles, and the squares, right? And it seems that the triangles are those cars that have low weight and high acceleration, and the circles are in between, and the squares are the ones that have higher weight and slower acceleration. Again, in this example, we're only using two features so that we can visualize them, but you can see the idea here. We have now three groupings uncovered from the combination of values of these two variables. What I am doing here, I'm basically recreating the plot, but adding the color to map to the miles per gallon. Again, I'm assuming I don't have access to this variable, but I want to do this plot so that I can see how my clustering is giving me some kind of insights about the kind of underlying relationship between these clusters and the miles per gallon. You can see here that the cars in that triangle cluster tend to have a higher miles per gallon compared to the to the circle cluster and the square cluster. Once again, this example is not a great example because I'm using two features. Ideally, I'd like to use more features, but then I cannot visualize them as easily as I can here. But ideally, I'd like to use all of the features to group my cars, and hopefully some of the car groups will give me some understanding of their fuel efficiencies. For instance, what I'm doing here, I'm taking the mean fuel efficiency per cluster, and you can see here cluster 1, which is the square, has the lowest fuel efficiency. Cluster 0, which is the circle, is having kind of a in-between fuel efficiency, and cluster 2, which is the triangle, has the highest fuel efficiency.